Hello APC Mechanics students. Today we'll solve the past paper of RQ 2023 Set 1, Exercise 1. Then let's start. Then, as usual, the exercise starts whenever we see the number 1, 2, or 3. Number 1, a block is sitting on a horizontal surface, is pushed against the spring P, that is attached to a wall compressing the spring, a distance x as shown in figure 1. The block is then released from rest. So the moment they mention it's released from rest, which means that the speed is 0, which means in the context of kinetic energy, the kinetic energy is 0. The block slides along the horizontal surface and up a ramp, reaching a maximum height h max p. Frictional forces between the block and all surfaces are negligible. The moment they mention frictional forces are negligible, which means that we can use conservation of energy along any 2 points, both on the track, on the horizontal track and the ramp. So here we don't have anything left. Then let's move to page number 2. A student compares h max p for spring P with the maximum height h max q achieved with a different spring q. Each spring exerts a force of magnitude F on the block that varies as function of the distance x that the spring is compressed as shown in figure 2. For spring P, the force is given by linear kx, where k is 100 Newton meters, and spring Q is given by nonlinear force, where c is given by 20 Newton per meter to the power of half, and the unit here is given like that in order for the force or for the constant c to agree with the dimension of the force and the displacement or the compression x. Now part A. So basically that's the graph. Now part A, for the experiment, the block is pushed against one of the springs compressing the spring at distance x is 0.01 meters. The block is then released from rest. In trial 1, spring P is used, and in trial 2, spring Q is used. On the following dots representing the block in trials 1 and 2, draw and label the forces, not components, that are exerted on the block at the instant the block is released. Each force must be represented by a distinct arrow. Starting on and pointing away from the dot, the lengths of the horizontal vectors should represent the relative magnitude of the horizontal forces, and the length of the vertical vectors should represent the relative magnitude of the vertical forces. Now, this is important. Why? Because we know that whenever we're drawing forces might be balanced or unbalanced, and one might be greater than the other. Then in this case, we need to take into consideration the relative magnitude. Now, as the block being placed on the horizontal surface, we know that the forces that are acting on the block, we have the pull of gravity down, the normal push, and the force exerted by the spring on the block. Now, always the force exerted by the spring points toward the equilibrium position. In this case, it would be pointing toward the left in each case for both springs P and Q. And also you can think about it in this way. The spring is pushing the block to the left, then the force would be pointing toward the left. Now first, let's represent the pull of gravity in both cases, because nothing changes, the block didn't change. Then the pull of gravity would be represented like that. Now the pull of gravity should be equal to the normal push because they are balanced forces. There is no motion up or down. And similarly here for both trials. And it is important, based on the instructions, that both the pull of gravity and the normal push should be balanced. Similarly here, because we didn't change the block, then the pull of gravity didn't change, as well as for the normal push. Then let me say that's the pull of gravity, the normal push, pull of gravity, and the normal push. Now in both cases, the forces exerted by the spring, in each case spring P and spring Q, would be to the left, but it's left to determine which spring exerts a greater force at the position given by 0.01 meters, and this can be determined by referring to the graph. 0.01 meters, which means somewhere here. If we go up, you notice that Q represents the dotted, then the force exerted by Q is greater than that of P, and it's almost the double. Then let's take that into consideration. Here we're gonna represent it, let me say 1, 2, 3, 4, so that would be 4. Then that would be F of the spring exerted by Q. Now it's not important to represent it to be exactly the double. The important thing is just to be greater, and that would be exerted by the spring P. So that would be FSP. And remember that it's important to label the forces by their names. Then this is it for part A. Now in part B, idea I, what features of the graph in figure 2 could be used to estimate the work done on the block by each spring as each spring is compressed? Now referring back to the graph, to figure 2, we know that each graph has certain features like the slope, the y-intercept, the x-intercept, and the area under the curve. In this case, if you look carefully, the area under the curve represents F times x, which is in Newton meter, which represents the work. And since we're interested in the work, then the feature of the graph would be the area under the curve. So here it's enough just to mention the area under the curve. Now in idea 2, there is one compression distance x0 for which the maximum height hmax reached by the block is the same regardless of which spring P or spring Q is used. Predict whether the value of x0 is greater than, less than, or equal to 0.04 meters. Use the graph in figure 2 to justify your answer. Now, what does hmax represent? Let's refer to the first page. Hmax represents the maximum height on the ramp that is being reached by the block. And this here, it is a gravitational potential energy, which depends on the kinetic energy here, and which depends on the elastic potential energy stored in the spring, which is US. So basically, it depends only on the elastic potential energy stored in the spring, which is basically the work done by the spring, because we know that these at some point they are equal. So it doesn't depend on the force exerted by the spring, but rather on the work done by the spring. And something important to note here is that whenever an exercise is split into idea 1, idea 2, idea 3, it means that these are related to each other. Now if you think about idea 1, in idea 1 we talked about the area under the curve, which represents the work done. So in idea number 2, it means that we need to use this notion in order to answer the question. Now referring back to 0.04, exactly at 0.04, both springs exert the same force on the block, which is given by 4 newtons, but for sure that would not be the correct answer, because this is so trivial. So it's either gonna be less than or greater than. For values less than 0.04, we can notice that the area under Q would be greater than that of P, which means that the work performed by Q is greater than P, which means that Hmax for Q would be greater than that of P. And that's not the case. Both areas would equate as P becomes above Q at a value greater than 0.04. For this reason, both works done by each spring would be equal for values greater than 0.04. And here, let's say, so x0 would be greater. Than 0.040 meters, because as the area under the curve represents the work done by the spring, both areas equate, so they would become equal for a value greater than 0.04 meters. And because both springs are doing the same amount of work. In this case, for a value greater than 0.04, then H max would be the same. Okay, this is it for idea number 2. Now in idea number 3, on the axis provided for both spring P and spring Q, sketch a graph for the maximum height H max reached by the block as function of the distance each spring is compressed for values x ranging from 0 to 0.1. Clearly label the curve for spring P and spring Q. Now it's first easier to start plotting spring Q. Let me explain why. Because spring P is a linear spring and it's given by kx, which means that if this is linear, remember that if we have the force, so if we have the energy and we do the derivative, we get the force, so they are related to each other via derivative, and that would be an integral. And we know that if the force is given by kx for linear spring, the energy is given by half kx squared. Now we are interested in determining the maximum height, and that would be done using conservation of energy, which is given by mgh is given by half kx squared. Now h in this case would be given as a constant a multiplied by x squared, which means that the curve of h as function of axis of x would be a parabola open up. But remember that both h max would be the same for a value greater than 0.04, so let me choose the value to be here. Now here we will make sure that both curves intersect. First, let me start by representing the curve of spring P. Now both curves would pass through this point because both works are equal and work would give me H max. Then let me draw it like that. So this is a parabola open up. Now that would be the spring P. Now we need to draw the curve for spring Q. Remember that, recall, for values less than this value, Q was performing more work than P, then H max for Q would be greater than that for P for values less than x0. Then I would draw it to be above the curve P so that they would pass through this point. Then it would be something like that. So that would be the curve for Q. Now here what is important for us is that this point should be clearly greater than 0.04. Before that point Q, the curve Q must be above P, and after that the curve P should be greater than that of Q. Now moving on to the next page, they're telling us spring Q is attached to the wall and is at equilibrium as shown in figure 3. Now let me copy here the characteristics of the spring Q, which are given by Cx to the power of half. And the value of C was given by 20 Newton per meter to the power of half. Let me double check. Okay. Now spring, alright, block A has a mass of 0.12 kg, block B has a mass of 0.070 kg. Block A is held at rest at the top of the ramp and block B is at rest on the horizontal surface. The student releases block A and it moves down the ramp and collides with block B. The change in vertical height of block A is h given by 0.75 meters. Now notice that here h, it's not being completely measured to the horizontal surface because we're measuring the difference in the center of mass, I suppose. After the collision, the blocks stick together, so the type of collision is adhesion or inelastic. and move to the right, compressing the spring. Frictional forces between the blocks and all surfaces are negligible, which means we can use the conservation of energy. Calculate the velocity of the two block system immediately after the collision between blocks A and B. So here we have two phases. Phase 1, which is energy, because block A, as it goes down, it will gain energy from gravity. Then after that they will stick to each other, and that phase 2 would be the conservation of linear momentum. So let me here start by writing the following. So apply conservation of energy. Energy initial would be equal to energy final. Here the initial point would be up top, and that would be the final point. Now the initial point, okay, we have kinetic energy initial plus gravitational potential energy initial, and that would be equal to kinetic energy final plus gravitational potential energy final. Now here I didn't include the spring because yet we didn't reach the spring. It is released, held at rest. The student releases block A, so it's obvious that we don't have speed, and whenever block A reaches the horizontal level, then the gravitational potential energy would be 0. And that means that M for block A multiplied by G multiplied by capital H, we should use the same notation, is equal to half mv square final. So here, let me say that would be VA, the mass and the mass would cancel. Then VA in this case would be given by radical to GH. And because it's a free response problem, it's better to use G to be 9.81 and H to be given by 0.75 meters. And plugging that on the calculator, we can find that V at the point A is given by 3.84 meters per second. Now, but that it's not the required answer, because we need to find the speed of the block system, block A, block B system after the collision, and this can be done using momentum. Then apply the conservation of momentum. Now here the conservation of momentum holds true because there are no net external forces acting on the system. Remember that in order for energy to be conserved, frictional forces must be neglected, and in order for momentum to be conserved, external forces, there must be no external forces. Now when A collides with B, what are the external forces on the system? We only have pull of gravity and normal push. We don't have frictional forces. Pull of gravity cancels with the normal push for the system AB, which means that we don't have any external forces, or the external forces are balance forces. Then now we can say that the initial momentum is equal to the final momentum. Now initially we have only momentum due to block A, and that would be 0. And finally we have, because they stick, we have a combined mass given by MA plus MB multiplied by the final velocity that we wish to determine. Then V would be given by fractional mass given by MA divided by MA plus MB multiplied by VA. Now we have the masses of the blocks, so V is given by MA, which is 0.12 divided by 0.12 plus 0.07 multiplied by VA, which we have determined, given by 3.84. And here you can notice that we will have a drop in speed due to the injection of inertia, and that would be 2.43 meters per second. Now in idea number 2, we need to calculate the maximum compression of the spring, and as usual, always and forever, whenever we have idea 1, idea 2, it means that they are connected, and the maximum compression of the spring can be determined again using the conservation of energy. Now blocks A and B, they are sticking to each other and they form one system. They will hit the spring will be compressed, and because we're talking about the maximum compression of the spring, then we assume that the speed at that point is 0. But the problem here is that the spring Q has a force given by Cx to the power half. So before we apply the conservation of energy, we need to make sure that we get the correct function which represents the energy of the spring, and that's determined via integral. Because remember that I said if we have an energy and that would be a force. So let me do it this way. If this is energy and this is force, we can do here derivative to get the force, but if we need the energy, we need to integrate. So in this case, we will say that the energy, the potential energy of the spring Q, can be written as an integral of the force of the spring Q, or let me say just Q for short, dx. And remember that in order to get the energy, we need to integrate over position and not time. So that would be the integral of cx power half dx, and that would be cx power 3 over 2 because we increase the power by 1 and we divide by the final power plus a constant c that we don't forget, and that would be 2c over 3 x to the power 3 over 2 plus a constant. So this function here represents the function which compensates for the energy stored in the spring Q. Now we can again say here apply conservation of energy. And we would say that the initial energy, which is the energy before the springs, before the blocks compress the spring, is equal to the final energy after the maximum compression. What do we have? We have kinetic energy initial plus the gravitational potential energy initial plus elastic potential energy initial, and that would be equal to the final kinetic energy plus the final gravitational potential energy plus the potential energy final stored in the spring. Now that would cancel with that because we're on the same horizontal level. Whether they are 0 or equal, we can just cancel them. Now we don't have any initial elastic potential energy because the spring is not being compressed yet, and the final kinetic energy would be 0 because the spring we have reached the maximum compression. Now kinetic energy is half mv squared, but about which mass we're talking? We're talking about the combined mass, which is ma plus mb. Then that would be half ma plus mb multiplied by v squared, and this is speed, represent the speed after the collision. That would be equal to the elastic potential energy of the spring Q, which is given by this expression 2 over 3 cx power 3 over 2, and we're interested in determining the maximum compression. So let's isolate x to the power 3 over 2. That would be given by 3 is down becomes up, 2 is up becomes down, ma plus mb multiplied by v squared. In this case, x would be given by 3 over 4. Let me do it here. X would be given by 3 over 4 multiplied by ma plus mb v squared, all of that to the power of 2 over 3, which is given by 3 over 4. The mass of block A was given by to be 0.12, and the mass of block B was given by 0.07 multiplied by the final speed, which is 2.43 squared to the power 2 over 3, and plugging that on the calculator as it is. Here I forgot C. C is up, should be down, so here we should have C, and here let me make some space and multiply by C. Then C is given by 20. X, in this case, the maximum compression, or just simply X, is given by 0.12 meters. Now finally, part D of this exercise, spring Q, where Fq is Cx power half, is replaced by a different nonlinear spring R, and the procedure described in part C is repeated. The procedure that is described in part C, that we place a block A at the top of the ramp and we release it from rest. Now we have 3 springs, P, Q and R. We have ignored P for the moment and we're comparing Q with R. Both are nonlinear springs of the same type, x to the power half, but one with the coefficient C and another one with the coefficient D. The maximum compression of spring R is greater than the maximum compression of spring Q. Which of the following correctly compares the constants C and D? Now C and D represents how much the spring is being stiff. the more the spring is being stiff, which means it is harder to compress given the same amount of energy. Since they're telling us that the maximum compression of R is greater than the maximum compression of Q, so let me put it this way, which means Q is being less compressed compared to R, which means the coefficient of Q, the stiffness, is greater than that of R, which means C should be greater than that of D. Alright? Now briefly justify your answer. We're doing this explanation or reasoning based on the fact that the procedure is described in C is being repeated identically for Q and R, which means that both blocks, before compressing the spring, they have the same amount of energy. Then let me state the following. The blocks are traveling at the same speed before colliding with a spring in each case. And this statement is important because we need to justify that both springs Q and R, in order to compare between their maximum compressions, they're being given the same amount of energy. Now we would say the maximum compression of Q is less than R, then the average force exerted by Q here it's important to mention the average force exerted by Q is greater than R. Which means then C must be greater than R. And by that we're done with the following exercise. So then C must be greater than D. So that's it for me in this video, guys. See you soon in a new one.